There is.
Okay, thank you. Can you hear? Okay. My name is Bercel Boldis from Hungary, Wigner Research Center for Physics and Budapest University of Technology. First of all, thank you for the organizers to giving me an opportunity to present here in this nice auditorium in the center of London. So, as it was introduced, my talk will be about determinant in supersymmetric gauge theories. This is a joint work with my supervisor Zoltán Bajnok from Wigner and Gregory Korczymski from Paris-Saclay. So, what I'm going to talk about in the next 30 minutes is first I introduce a bit the ADS-CFT correspondence, or more like its parameter space, to be more able to understand what our results are. I'm pretty sure that most of you are familiar with ADS-CFT correspondence. But anyway, and after that, I will talk about these so-called determinant observables. First in general, and after that I separate them to two different classes based on 3 papers from the last year. So let's go. So first, as I mentioned, ADS-CFT correspondence. So ADS-CFT correspondence connects quantum field theory on a flat background with one on a geometrical background. Especially in case of the usual ADS-CFT correspondence, you have the ADS5 space on one side, and what you find is geometrically it has a conformally flat boundary, and then you can take some conformal field theory, especially N equals 4 super Young-Mills theory on the boundary, and what you find are the observables in this conformal field theory are can be related to string theory observables on the ADS background. So it's okay, but we have like several parameters in the two theory. For example, string tension, Young-Mills coupling, also the rank of the gauge group, since N equals 4 have this nice SUN gauge symmetry. After that, matching everything together, mixing them, you will have effectively 2 important parameters. One is the rank of the gauge group, or 1 over the rank of the gauge group. This is, I denote this by NC here, and the Toft coupling. So in the next, in my presentation, I will talk about the planar limit, mostly the planar limit, which is the n goes to infinity limit, so leading order or next to leading order in it. So we killed one parameter. The other one is the Toft coupling, which we are interested in. So in this case, we have like 2 different choices what we can consider. Either we can consider the weak Toft coupling limit or the strong Toft coupling limit. So from the weak side, you can basically do perturbation theory in the conformal field or the gauge theory. This is the red curve here. Or from the strong side, you can do with some magic perturbative string theory. But what's the main point of the ADS-CFT correspondence? In the middle, if you are precise enough or get enough coefficients, you will have some matching in the middle. But of course, since these are just perturbation theories, you will never have an exact matching, but you can try. And of course, there are some other problems as well. So in most of the cases, if you do perturbative gauge theory, you will have a finite radius of convergence after adding everything up. So it breaks down at some certain value of the Toft coupling. And also there are some problems from the string theory side, because you find that if you take the perturbative series, you will have factorially growing coefficients, which means that the series cannot give you any meaningful physical quantity, and you can also contain exponentially small perturbative corrections. So what I will talk about is exactly this strong Toft coupling limit, And I will explain in certain cases for this determinant observable how you can compute effectively to any order the 1 over lambda corrections and the exponentially small corrections. So what are these determinant observables? I will explain what this determinant means, but first I will just list some of the examples what we considered. So for example, as I mentioned, in most of the cases we are investigating the n equals 4 super Yang-Mills theory. There you can construct some physical quantities, for example, the cusp anomalous dimension, which comes from the expectation value of a Wilson loop with a cusp, or the octagon form factor, which is some 4-point correlation function of special operators. But you have also like scattering amplitudes. Also, there are some different models. For example, n equals 2 super Yang-Mills theory, where you find similar quantities. Also, there is random matrix theory, where you find a similar quantity, the Tracy-Widom distribution, which gives you some eigenvalue distribution of random matrices. But each of these quantities have something in common. And this is that for arbitrary Toft coupling, which I will, from now on, I will denote them by G because it's more suitable. In each of these cases, your observable is given by a determinant of semi-infinite matrix. So first, I will talk about those quantities that we considered in these two papers. For example, the octagon form factor in n equals 4, or the free energy on the sphere in n equals 2. And so since this is only the second talk and we already had a coffee break, I will get a bit more into technical details, but I hope it won't be too much. So what we are interested is that the strong coupling expansion of these determinants. So each of these cases have the same structure. The matrix elements of the semi-infinite matrix K and M is given by an integral of some Bessel functions and some symbol. I mean, it's just a function. I will refer to them as the symbol of this problem. This function chi can be chosen arbitrarily. So in each cases, you have the structure integral of Bessel functions put into an infinite matrix and calculated its determinant. It sounds like a very hard problem, but with some modifications or tricks, you can make it easier to deal with. So as you can see, you have also another parameter, this curly L, and by fine-tuning this chi symbol and this parameter L, you will have different observables in different theories. So let's talk about this symbol. So this is actually the essential part, how you can get the non-perturbative coefficients to understand its analytical structure and so on. So if you do some Wiener decomposition of this symbol, I will denote this with phi. So this phi has only poles and zeros on the positive half plane. So you can do this, also introduce the small x behavior of this function and so on. You can break down the whole problem into these kind of parameters even more, not functions now, only just parameters and numbers and so on. So here you can see the previous three examples. For example, you have this L parameter, and also you have the location of zeros denoted by xn and the location of poles. Actually, what will be important for us is the location of the zeros of this symbol function. So previously, it was shown by Belitsky and Korczemski that how actually the strong coupling expansion of these determinants behave. So there are some terms, divergent terms proportional to G or log G. There are some constants. It was previously defined. And there is the perturbative part, which goes in powers of 1 over G. So they already calculated and built up some very nice machinery to calculate these perturbative coefficients a, k plus 1. They contain, as you see, the parameters that we define and some integrals over the symbol. You can just leave it like that as also as some parameters or something, or calculate it numerically. Anyway, the main point is that they gave a machinery. I will talk about in more details how you can determine these coefficients, getting the whole perturbative part of the observables. But if you put in, so like choose one specific example from these observables and put in these parameters, you will find that actually these coefficients grow factorially, so they cannot have any physical or mathematical meaningful resummation. So you need to include exponentially small corrections as well. And this is denoted by delta f here, and they goes, actually we will see how this actually goes, but they contain these exponentially small corrections, contain exactly the location of the zeros of this symbol function. And it is an infinite series of exponentially small corrections, and at every exponential level, you have infinitely many 1 over g corrections as well. So it's quite a huge problem to effectively get these coefficients up to any order in also in exponentially and also in 1 over g. So what their method was based on to get the perturbative coefficients. First, they rewrote the infinite matrix to an integral operator. Why is it good? So like this is an integral of also of the Bercel function acting on the function. This is how this integral operator acts. Why is it useful? Because now you don't have like matrices and so on. You can instead use functional relations and derive some differential equations, integral equations for these quantities. This is called actually, so if you rewrite this observable as a determinant of an integral operator, it is defined in some way. I don't want to go into very deep details. This is called the Fredholm determinant. And every observable that I will talk about has this nice Fredholm determinant structure. So how we can approach this problem? We need to introduce some other stuff which will be useful and not just some ad hoc things to define. So you can define with this integral operator the resolvent, for example, the resolvent function sandwiched by the position and one state, one Bercel function. This will be quite useful since we know a lot the analytic properties of this function. Right? We denote this resolvent function by this qx function. What can you derive from the definition, from the integral operator definition of this function? First, you can derive some integral equations. This is very nice because actually it is not only one integral equation. It is an infinite set of integral equations, and you can solve them by some mathematical methods. And what you get is you get some ansatz for this resolvent function. The structure is quite important because you see you have some oscillating factors, also have this age xg. You don't know anything much about it, but you know that it is an infinite series of infinite series, exactly going with the same exponential corrections as our determinant, and also going with powers of 1 over g. So if we can somehow determine these HKN coefficients, that would be nice. What is important is that we also have, somehow if you solve this integral equation, you see that the symbol appears inside the integral as well. So if you solve this equation, you will find that you will have this phi, the decomposition of chi, in the denominator. So somehow the zeros of this symbol function will appear as poles of, in this auxiliary resolvent function. So this is the first ingredient that we need. The second ingredient is also coming from these nice functional definitions. You can derive a differential equation for Qx, but what's important is that this differential equation now contains also our observable. So now we have something that we can effectively solve order by order. It's just a second order differential equation, so you can put it into mathematical solve order by order. But what's important is that this will give you relation between the observable itself and our newly defined function Qx. So this is what I wrote here. So somehow the coefficients in Q, H, K, N can be expressed in terms of the original problem, the coefficients in the original problem A, K, M. But this is not all. You also have some other relations as well. You also have an integral equation which also contains the observable and this Q function. This is actually, I think it's very nice that you have so many things relating these functions and everything, but this can also be solved order by order, just by hand or by Mathematica and everything, and giving another relation between these coefficients. So now you have basically two unknowns, HKM and AKM, and two equations. So that's in theory enough to solve everything. Of course, you need some boundary values as well to solve this, and it turns out that it's extremely hard at some point at some exponential levels. But in theory, if you have these boundary values, like the starting value for AK at each exponential level, I think you could solve it only just by these ingredients. So this was actually enough to solve the perturbative part of the observable. Now we can go toward to see how we can determine the non-perturbative coefficients as well. So this is what we call quantization condition, but it has nothing to do with quantization. It's just a nice fact that since Qx is an entire function, it has no poles. So if we multiply this function with this combination, which has Qx, as I mentioned, have these poles in theory at first guess. If I multiply with this symbol, which has zeros exactly in this location, in this limit, when we go to the location of these zeros, the residues should disappear. What happens actually when you substitute this value into this function? As you can see from the oscillating part, you will have exponential corrections exactly in the middle of the exponential corrections what we are looking for. One half level up from this part and one half level down from this part. So since they should disappear, you can match these coefficients, make them to 0, and what you get at the end of the day, what is the main message? That now you will have some very easy equations very simple equations to connect the exponential levels in H to the perturbative level of H. Now, since the exponential levels in H are expressed by the original AKN functions and the perturbative part of HK are expressed by the original AK coefficients, now you have like simple equations to express the relation between them. And actually, this is enough now to just put these locations and express the non-perturbative coefficients very efficiently by the perturbative ones. So this is the method what we used. So this is 4 steps. Each of them seem to be very difficult, but I put it in a flowchart. Actually, this is what we used in Mathematica, and it turns out that it can be used very efficiently. I mean, you just need to solve order by order this stuff. It do it very fast, and then just put it into the quantization condition, and you can get any corrections in 1/g and any exponentially small corrections. I mean, of course, it will take some time if you want it analytically, but we also made some numerical tests, and we get, I don't know, to 5 exponential levels, hundreds of 1/g corrections to thousands of digits of precision. So you can see here some results. By this method, we were able to reproduce some previously known actually resummable functions, which is nice. And here you can also see some analytical results for example, the octagon form factor or the n equals 2 observables. So what is important, so why we tested it numerically with such a high precision is that, for example, we wanted to investigate its resurgence structure. What is resurgence in a nutshell? I won't have time to go into more details. So if you have a function, actually an analytic function that have this expansion in 1/g, in sometimes, as in our case as well, you can get the coefficients. If you do perturbation theory or something, you can have coefficients with factorial growth. So here I put here some quite general behavior. So you have like if you investigate the behavior of infinite these coefficients, you can also have some nice expansion in k, factorials of k, and some powers as well. But what is important, that if you want to resum this series, you find that it's divergent since their coefficient grows factorially. So what you can do, you can just divide them by this factorial. This is called the Borel transform. I denote this newly introduced function as BS. This is the Borel function. It also has some inverse. So if you would have like not a factorial growth, but some nice convergent series, you can transform it to the Borel plane and then transform it back, no problem at all. This is the inverse transform of this Borel transform. What you see, what is important is that it is given by an integral of this Borel function. Okay, but since our coefficients in f grow factorially, it turns out that the coefficients in the Borel function will converge to somewhere, which will be, I mean, the series will be convergent, but only for specific values. What you get is that this BS exhibits some singularities at some certain real values in the real line, in the positive real line. So it is not obvious how to do this integral, because it goes from 0 to infinity. If you just want to integrate it out, you will hit the pole at somewhere, which is not good at all. So you have some ambiguity. What you can do is you tilt a bit this integration contour a bit above the singularities or a bit below, but this gives you some ambiguity how you can transform back your Borel function. And actually, if you do this whole machinery more precisely than you can see here, you find that the ambiguity, the difference in these ambiguities will be exactly proportional to some exponentially small corrections. So these exponentially small corrections are necessary to kill these ambiguities to have some meaningful not divergent series. So what we did, so we had so many numerical values and so on. We checked that this resurgence actually work for these observables as well. So we connected these C0, C1, C2 coefficients to the next exponentially small corrections, and also checked whether resumming everything will give you or converge to the exact values. Okay, so this was the first class. I don't have so much time, but I want to talk about the second class a bit as well. This is from our third paper, and this is another class of these determinant observables. Here the structure is a bit more like difficult, because now you have a determinant of not just an infinite matrix, but a block, a 2x2 block of 4 semi-infinite matrices. So how you can compare to the previous one? In the previous case, you only have like, by tuning this L parameter, this curly R parameter, you only had either odd or even Bessel functions. Now you have some rotation in the subspace of even and odd Bessel functions. So by what you can find is that by fine-tuning this alpha parameter, which rotates you in these subspaces, you can get some other observables like the cusp anomalous dimension of the octagon, or in case of this gluon scattering amplitude, some other alpha appears with rational R. So this is also exact for arbitrary Toft coupling. So we investigated this case as well. What you find is that now you have two exponentially small scale, this lambda minus and lambda plus. So we wanted to calculate or apply our previous method exactly to every order in lambda minus and lambda plus. We did the same machinery actually, just it was not like only integral operators, but 2x2 matrices of integral operators. It was a bit more messy, but everything worked fine as previously. So we were able to determine non-perturbative coefficients. So here the properties are not important. What is important that you also get factorial growth. So it is just a formal transseries, and now we can also investigate resurgence and anything. So it turns out that instead of investigating this F observable, it's more simple to consider. It's exponential, which I denote this by ZL. Not by accident, it's actually related to a string partition function in the dual theory or some other string observables. And the leading order is given by the semi-classical result, and you can get some subdominant saddle points, and this correction will exactly give you those corrections in the dual ADS string theory side. So we investigated the resurgence structure of these coefficients, and what we found is quite, I think it's quite interesting, because in case of this string theoretically meaningful function, you have some disappearance of the perturbative coefficients, and these arrows, what you can see here. So in the Borel plane, you have some certain poles at each level. This means that in theory, like lambda minus to the 0, lambda plus to the 0, the perturbative part could communicate to any of the non-perturbative coefficients, and also can communicate via 1, 0 and 1, 1 with 3, 2 or anything. So in general, you should have some nasty structure of resurgence in this case, especially since you have two exponentially small scales. But it turns out that not everything communicates with everything, and we found this nice structure. We don't understand it yet, so it's a further plan to see what is the resurgence structure behind. I mean, not the resurgence structure, but the whole mathematical stuff. Why this happens, and also what is like the string theory meaning of the disappearance of some coefficients and the relation between them. So I want to conclude my presentation with this feature. So this is for the tilted cusp. Here we plotted the V coupling expansion, the strong coupling expansion, and the exact results coming from matrix truncation for different values of parameters L. And if you remember the first, the sketch on the first or second slide of my presentation, this exactly shows that with these non-perturbative coefficients and strong coupling, we can go very, very close, like with 10 to the minus 20 to the exact results. So this is what I wanted roughly to tell. So we investigated some observables in n equals 2 and n equals 4. We investigated their strong coupling. We gave a systematic method to get the coefficients to arbitrary order, also in 1 over g, also in the exponentially small ones. We did some numerical verifications, checked the resurgence properties. So what we can do, we don't know what is the dual description in each of these cases. How can you get these coefficients, for example, from string theory calculations? We can also investigate some other limits of the octagon form factor, also investigate the resurgence structure a bit more deeper. There is a whole mathematical machinery behind that, what we don't really understand yet. And also there are other theories, for example, the ABJM theory, where some Fredholm determinants and these resolvent functions seems to be quite useful. So thank you for your attention.
Okay, we have time for a few questions. Right there in the middle.
Thanks for your nice talk. I want to ask a question about the last two slides about the partition functions. Yeah.
This one? Yes.
Yeah. When you say compared to the string theory side, that's a flat space string or ADS string?
ADS.
Okay, but I don't think people have the real ADS string theory.
No, that's what I mean under we don't know what are the dual meaning of this graph, or maybe I don't understand the question correctly.
So this is a prediction of what this string theory in ADS should be.
Yes.
Okay, thank you.
I mean, there are some certain cases which are more simple, like some Wilson loop on the n equals 4 side, where it was actually done. I mean, there they were able to calculate the string theory correction, the exponentially small correction, and there works. We checked that, but that is very simple, and that's all we have right now. So yes, it's a prediction more like.
Okay, thank you.
Thank you.
Koya? You have a booming voice. You can probably, you don't need the mic.
So what you actually call cusp is not a cusp, it's like just phi square coefficient of it, right? Or theta square coefficient. What you call cusp?
The cusp anomalous dimension. I mean, like if you renormalize.
Yeah, but it's not the function of theta. It's just theta square coefficient. That's Bézier over Bézier. What you probably speak about, right? Bézier I over Bézier I. So my question is whether you can also pack phi to the 4 coefficient, which is also known analytically to any order. Well, analytically the function of G into the Fredholm determinant. Because that would be highly non-trivial, I guess.
Yeah, sure. I couldn't comment on that right now. I mean, good question.
All right, let's thank Bercel for this talk.